Welcome to ECE476, lecture number 16, Edge Interrupts. Now in this lecture, we're going to look at more efficient ways of keeping track of edges so that every time I press a button, I can record it right away rather than using polling. That's an interrupt. We'll be able to simulate a stoplight. Every time you push the button, the light changes. We'll be able to play a reflex game. When I press the button, I'll turn on a buzzer 4 to 7 seconds later. As soon as the light turns on, I'll press the button, record the time of that button push. And with that, I can measure your reflex time much more accurately. I'll be able to interface an optical encoder. That's over here. So as I turn a digital potentiometer, I can increase a count or decrease a count. And finally be able to replay the old video game Pong. I tried to reflect a ping pong ball back and forth. If I hit it with the paddle on the left-hand side of the screen, it reflects. If I miss it, game's over and need a quarter to play again. So that's kind of where we're heading. Kind of use edge interrupts to record the time of to record edges when they happen, and with that, have some fun. So, let's start out. Now, interrupts are a strange beast, but they're really, really useful. An interrupt is a subroutine that's called by hardware. That's kind of odd because someone else is calling subroutines in your program. Interrupts are really powerful, however, so if you can figure them out, you can do all sorts of things. The microchip that we used in embedded systems had interrupts. Not too surprisingly, the Raspberry Pi Pico also has interrupts. In this lecture, we'll be looking at edge interrupts, when you might want to use them, and some things you can do with edge interrupts. So let's start out with polling versus interrupts. So far, we've been using polling. If I want to look for button push, I check the button, say every 10 milliseconds, and then if I see a 0-1 transition, I detected a rising edge. A 1-0 transition was a falling edge. Now that works, but it's really inefficient. I'm constantly checking the I/O pin, seeing what the logic level is. So it seems like there ought to be a better way to do it, and there is. That's interrupts. With an interrupt, what I do instead is I just call the subroutine when needed. I just call it on the rising edge or the falling edge. That leaves the main routine free to do whatever you want. Only call the interrupt when you need it. But this makes it kind of strange. This is a subroutine that's going to be called by hardware, not by software. So the fact that hardware called the subroutine rather than software is going to create a problem. In Python, we know how to pass parameters to a subroutine that I call. That's like our print command, various things like that. Well, how do you pass variables or pass data to a subroutine you didn't call? That's where global variables come into play. Back in Computer Science 1, you're told never, never, never use global variables. Global variables mess up your logic, mess up the program. For example, if I had a counter n as a global variable, and this for loop used n, this for loop used n, it gets really hard figuring out what's going on. That's one of the reasons you're not supposed to use global variables. It messes up your program, makes debugging just a pain. But sometimes there is no choice. If I want to pass data to a subroutine that I didn't call, I kind of have to use global variables because everybody can see global variables. The subroutines I call can see them. The subroutines I didn't call can see them. So in this course, go ahead and use global variables. They can be useful and sometimes they're necessary. So let's start out with just a single edge interrupt. I am going to push the button, GP15, and when I push it, I want to detect the rising edge or falling edge. Let's, in terms of hardware, have the button tied to ground with the internal pull-up resistor. When I press the button, I get a falling edge. So let's count the falling edges on GP15. Well, the way I do that with interrupts is the following code. I have an interrupt service routine, be any name that you like. This is what happens when I detect a falling edge. In this case, I'm going to set a flag and increment a counter. I've got this section of code that sets up pin 15 as an edge interrupt. So pin is pin 15. Pin is set up as an interrupt. I'm going to trigger on the falling edge, and when I interrupt, I call this subroutine. I call interrupt serve. Then the main routine, this is where the magic happens. I've got this variable flag, variable n. It looks like from the main routine that flag and n should never change. They do change, but that's the interrupt. Every time I press the button, I call this by hardware. Hardware calls this. That sets flag, sets n. They're both global variables, so the main routine can see that. If the flag was set, then I'll print n. So the reason for the flag is instead of just printing all the time, I'm only going to print when I need to print, when n increased. So for example, I've got the following program. The main loop is just waiting for flag to get set. When I press the button, press, release. As soon as I pressed it, it went low. That triggered the interrupt. N incremented, flag incremented. So press, release, press, release, press, 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 press. That's an interrupt. The hardware is calling the subroutine, and what's nice about it is I'm able to count button pushes. Now that's using the shell window. If I want to use the graphics display, I'm going to get rid of this subroutine. Basically, while 0 means ignore. Same thing with the graphics screen. I'm going to display the count on the graphic window. And I'll increase the bar chart, showing how many button pushes I have. That's an edge interrupt. Now back over here, I can make it rising edge or falling edge. On a falling edge, that's when I push the button. On a rising edge, that's when I release. So back over here, now this rising edge, you go press, release, press, release, press, release. I'm getting some double counts. That's the debouncing. I can also count both edges. So here I'm counting the rising edge and falling edge. They'll both trigger the interrupt. Press, release, press, release, press, release, press, release, with some bouncing issues. So that's basically the edge interrupt. And a couple things to note. I am passing data between the main routine and the interrupt service routine using global variables. It's about the only way to do it. I can detect rising edges, falling edges, or both edges. And I'm using a flag. The flag, it just tells the main routine, only print when needed. So don't have a whole string of numbers showing up on the screen. They only change, only just update the display when the number changes. Another thing to note, with interrupt service routines, keep it simple. The next interrupt could be coming really, really fast. So don't do any loops, no while loops, no for loops. Just get in, get out. For example, this routine, all I do is set a flag, increment a counter, leave. That's because very shortly in the future, I might have another interrupt coming. So that's kind of the basic idea behind edge interrupts. Some things you can do with it. Let's do a stoplight. So this is going to be a manual stoplight. I have to push the button to get the light to change. So if I'm at yellow, red, press the button, it goes to red, and red, red then green, yellow, red, green, yellow, red, and so on. Same idea as before, but I'm going to use the push button to control the light change. Later on, next lecture, we'll use timer interrupts to change the lights, but we haven't gotten to that yet. How to write this program, and write it using bottom-up programming. It's a step-by-step approach to writing a program. So the first thing we're going to do is get the display routine to work. That displays these lights. So this would be red, green, yellow, red. Rectangles, because rectangles draw faster on this board. This is my display routine. The reason I'm starting with the display routine is it helps me write the rest of the code if I can see what's happening. So I'm going to pass it to it the number light. 0 is red, 1 is yellow, 2 is green, kind of arbitrary. And where I want the light to be, which light I want to draw. I am going to define the colors: red, yellow, green, brown, black, white. Draw a solid box, that's the outside of the light, and then a box with a line around it. If I'm doing a red light, the top light is drawn in red. If it's a yellow light, the second light is yellow, otherwise black. If it's a green light, third light is green, otherwise black. Once you write the code, test it. So this would be a little test routine. I can go from, let's see, display 0, that'd be red, 2 is green, run it and see if it works. So sure enough, the first light is 0, that's red. The second light is green. Looks like the display routine's working. Okay, now that that works, let's check out the light sequence. I want to go from green, red, yellow, red, 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 green, red, yellow, red, red. Verify that works. So here's my ring counter. It counts once per second. If the count is at 0, I'll display green, red, or yellow, red, 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 and so on. See if that works. So check to see if that works. So here's the code running. Every second the light changes. It's going green, yellow, red, green, yellow, red. All right, that looks good. Now that that works, add the interrupt. Every time you hit a button, I'll count mod 6. So back over here, every time you hit the button, the light changes. So there's your green, yellow, red, green, yellow, red, triggered by the interrupt. So there's a couple of problems with this routine. One, you have to manually push the button each time you want the light to change. So that's a little bit inconvenient. We'll fix that later when we get to timer interrupts. And sometimes you get multiple counts due to bouncing. We can fix that as well. So bouncing is a feature of mechanical switches. When you push the button, I get multiple edges. So what that shows up as is you get multiple counts on a single button push. You can eliminate that with debouncing. Now debouncing can be both by hardware and software. For hardware, what I do is I add a capacitor. What the capacitor does is when I push the button, in this case it discharges down to 0. When I release the button, it charges up with an RC time constant. So here, if I keep it large enough, it doesn't have time to charge up, and I don't go past logic level 1, it stays at 0. When I release the button, it tries to charge up until the chattering stops, then it charges up. Again, I just get a single rising edge count. In terms of the timing, the RC time constant, you can check on an oscilloscope and see how long it chatters. If this is like 10 milliseconds, then pick the RC time constant to be about 10 milliseconds. So with the internal pull-up resistor at 50 to 65K, they make C between 0.15 and 0.2 microfarads. That's a hardware solution. In software, what I can do is I can set up a 10 millisecond wait. When I detect the edge, I ignore all subsequent edges for 10 milliseconds. And then I check. After 10 milliseconds, is the line low or high? If it's low, that was the falling edge. If it's high, that was the rising edge. And I need to do that because if I'm looking for falling edges, I'm going to get falling edges over here due to bouncing. Those are kind of stray ones I want to ignore. If I check 10 milliseconds later, the line was high, that was bouncing, ignore it. Over here, the line is low, that was really a falling edge, count it. Third way I can do that is a sleep statement. When I call the interrupt, I'll wait 10 milliseconds and then check. Somebody triggered the interrupt. Was it rising edge or falling edge? If it was the low, that was the falling edge, count. Now that's kind of inefficient. 10 milliseconds is a long time. That's like 10,000 clocks at 1 megahertz clock. It does work. There are better ways. but the better ways use timers, which we'll get to in our next lecture. So, now that we have edge interrupts, let's have some fun. Let's play a game of Hungry Hungry Hippo. Now with Hungry Hungry Hippo, I've got a bunch of players. When the game starts, you thrash your button as fast as you can. Whoever gets the most button pushes, or most dog treats, wins the game. And the game only lasts for a fixed amount of time, so we're going to play for 10 seconds. Any button pushes after 10 seconds are ignored. So how do we do that? Well, there's hardware and software. For hardware, to make the push buttons read, I'm going to use an internal pull-up resistor and a push button tying them into ground. That's on the hardware side. On the software side, I'm going to set up two interrupts. There's going to be player 1 and player 2. Now player 1 is tied to pin 15. That's handled by this guy on the falling edge. I'll call interrupt subroutine player 1. That increments counter N1. Pin 14 triggers interrupt service routine player 2. That increments counter N2. So as I play the game, I'll just count really fast. So here's what that looks like. I've got my two scores. There's the time, player 1, player 2, player 1, player 2. When I get to 10 seconds, the game's over. I can also do that using the graphics display. Same idea. I'll display the two scores. First one's in pink, second one's in cyan. Plus, I'll do a bar graph. That's the time left in the game. So as the game is running, see, here's the time left in the game. Here's the running scores. They'll keep track of the counts until this time gets to 0. A couple double counts in there. When the time gets to 0, it quits counting. So here we're still counting. Game's over. Oh, that was a close one. So notice there's a little bit of problem with this game. The game isn't exactly 10 seconds. The reason being is I've got my wait loop. The wait loop is probably dead on 100 milliseconds, plus the time for all the rest of the code to execute. So back in Thani, this is 100 milliseconds. I've got to take into account all this time as well. Well, that can actually be fairly significant, so my timing's off. To fix the timing, I need to use a different approach, like timer interrupts. That's our next lecture. Once I'm able to record number of button pushes for 2 or more players, you can do some variations on the game. I can display it on the LCD display, like I just showed. I can do the difference in score, have like a tug-of-war game. You know, a bunch of options there. Another game I can play, a reflex game. So here's the idea. To start the game, I hit the button, the light turns on, the sound comes on. As soon as it comes on, I hit the button, and it measures the time between when the light turned on and I hit the button. So that was 3.5 seconds later. Not very good. Try it again. It picks a random number between 4 to 7. And I hit the button 198 milliseconds later. Try again. So, how does that work? What I'm going to do is wait for the button to be pushed. When it's pushed, I'll set up a counter, 3 to 7 seconds, turn on a light, turns on the beeper, then I measure the time of the button push. What the code does is I've got a global variable T1, that's the time that I hit the button, a flag to tell the main routine that the button was pushed. In the main routine, I then wait for the flag to get set and I hit the button. When I hit the button, it picks a random number between 3 and 7 seconds later, sleeps that long, clears the flag, waits, turns on the buzzer, waits for the flag to get set, and I hit the button, record that time. Once I record the times, take the difference in time, that's my reflex time. In addition, I can use the graphics display. So come back over here. I can clear the display. I'll hit GP15 to start, hit the button. The buzzer comes on 4 to 7 seconds later. Hit it. That was 258.246 milliseconds later. Try it again. $222.115. Try it again. 586.9697. I've got a reflex gain. Another thing you can do, you can use optical encoders as a way to get input to your PIC board. Now, there's a couple types of potentiometers. There's analog and digital. An analog potentiometer is basically a coil of wire. If I tie this to 3.3 volts, tie this to 0 volts, then the voltage will be increasing as I go around. This is the wiper, the center tap. As I turn the wiper, I'll go from 0 to 3.3. So with that, I can measure angle. That's one way to do it. Another way is a digital potentiometer. What that does is this outputs two square waves in phase quadrature. By counting edges, I know how far I've turned. By counting edges in direction, I know which direction. For example, if time goes left to right, on the rising edges on A, B is low. On the other hand, if time goes the other way, if this is time, on the rising edges, B is high. So by checking whether B is high or low on the rising edges, I know direction. In terms of coding, there's a couple ways to do that. If I just look at channel A, I can count both rising edges and falling edges. The encoder I'm using actually has 200 pulses per rotation. That's for rising edges. If I count rising and falling edges, it's 400 pulses per rotation. I need to come up with some logic. So if B is high on the rising edge or low on the falling edge, then I'm going backwards. Otherwise, I'm going forward. That's what this logic does. Put that in an interrupt. I'm going to interrupt on rising edges or falling edges. Every time I interrupt, I increment or decrement a count. Display that count. So here I just have the single interrupt calling channel A. I'm going to increment or decrement a count. So this is the time, here's the count. As I spin it clockwise, here's one rotation, 500, that should be 500 counts per rotation. Here's 2 rotations, 3 rotations, 500 counts per rotation in the forward direction. This encoder actually has 250 pulses per rotation. Go backwards, and I'm counting back down to 0. Now if I just count on channel A, I get twice 250 or 500 counts per rotation. If I count on channel A and channel B, spin around once, I get 1,000 counts per rotation. 3, 4, 5, and going backwards, I can now count angle. So I can get data to my microprocessor using optical encoder. That's both counting rising and falling edges. With that, I can build a Pong game. So what the Pong's doing is this controls the left paddle. As I turn the optical encoder up and down, I can move the left paddle. What I'm going to try to do is have the left paddle match up with where the ball is. That causes a reflection, and I get a point. So the first thing is I've got to get the paddle working. This will be the paddle. I'm going to input a number from the optical encoder, 0 to 320. That's the Y location of the paddle. I am going to clip it if it goes out of range, and then define a rectangle that goes from 0 to 320. I'll initially make everything black. That is 0. Wherever the paddle is, if this is Y, the paddle, I'll go Y plus 20, minus 20, and make that white. That's what you're seeing over here on the left. That's where my paddle is. I can move it up and down. Next part of the game. This is the old bouncing ball program. I've got the ball bouncing around the screen. There's the position X and Y. Here's the velocity X and Y. I bounce around. If I hit the right side, it reflects X. Top, go down, bottom, go up, and beep. If the right side bounces left. If I hit the left side and I hit the paddle within 20, it reflects. Otherwise, game's over. I get 1 point every time I hit the paddle. So I'm not doing real well. So you can kind of build a fun game like Pong. So that's kind of some things you can do with an edge interrupt. With edge interrupts, well, with interrupts in general, they're kind of confusing, but really useful. With edge interrupts, you can call a subroutine only when needed, such as when you detect an edge. With that, I can keep track of number of edges more accurately. I can count edges much faster. And with an optical encoder, I can measure angle. It's a way to get numbers into a microprocessor. Using edge interrupts also really simplifies the code. For example, back over here, to count the edges, this is actually pretty simple. I just increment or decrement a counter. I don't have to look for the 0-1 transition, remember the old data, crap like that. Just call the interrupt when I need it, on the rising or falling edge, or both. The trick with interrupts is you almost have to use global variables. That's different than what you took back in Computer Science 1. We were told never, never, never use global variables. Here you kind of have to because you're using a subroutine that you didn't call. But if you can figure it out, interrupts are really useful, they're really powerful. So that's lecture number 16 for ECE476.